So let's go ahead and talk about exponential functions and then logarithmic. So let me grab my actual notes here. So here's the idea. We want to graph something like, so this is exponential. And I really want to clarify, because I feel like people kind of get confused by the language here. When we say an exponential function, we mean a function where the exponent is a variable. So something like y equal to a to the x power. Some examples of this, which we're going to graph in just a moment, would be like y equal to 3 to the x, or y equal to 4 to the x. And so the variable is an exponent. There are some restrictions on what the base is allowed to be. The base should not be 0. That would be boring, right? 0 to any power. Well, if it's a positive power, 0 to any power is 0, right? 0 squared is 0, 0 cubed is 0, and so on. If it's a negative power, 0 to a negative power is actually undefined because you're divided by 0. So we don't want the base to be 0. We also don't want the base to be, the base should be not only not 0, it should be positive, because negative numbers are a problem. And then the base should also be not equal to 1, because 1 to any power is just 1, so it's more of a constant function than an exponential function. But yeah, we don't want negative numbers, because negative numbers to fractional powers are undefined sometimes. Like, for example, if a was -4 and x was 1/2, -4 to the 1/2 is the square of the -4, which is not real. So we don't want bases that are negative, so that we avoid the problem of having a restricted domain. My voice feels a little scratchy. And I can't say why. It's not like I feel fine, but my voice just feels a little not excellent. So let's see. A couple other things here. Yeah, let's actually graph the first one here. So as with graphing, sometimes we like to be more precise than others. When I graph an exponential function, my go-to is kind of just to be like, I know it has this sort of shape. Now we can be very specific a couple times. If I was going to plot some points, if x was say 0, 1, and 2, y would be 3 to the 0, which is 1, 3 to the first, which is 3, and 3 to the second, which is 9. So I'm going to start plotting points here. We see that, all right, well, let's see. I get the point 0, 1, 1, 3, 2, 9. Things are escalating very quickly here. I don't have a vertical asymptote, but it kind of starts to look like I do, but we don't. And then to the left, if x is -1, 3 to the -1 is 1/3. And if x is -2, 3 to the -2 is 1/9. So to the left, the values get smaller and smaller and smaller, but they still stay positive. So a couple things to note. We have, this is going to be true for any exponential function. We have a y-intercept always at 0, 1, because anything to the 0th power is going to be 1. We have no x-intercept. We have a horizontal asymptote at y equal to 0. Right, so as we go to the left, the function gets closer and closer and closer and closer to 0, but it doesn't actually ever touch the x-axis. And we have a no vertical asymptote. So these are things that are true no matter what your base is. If it's 2 to the x, 3 to the x, 1/5 to the x, 99 to the x, right? Any positive base that's not 1, right? So as long as you're meeting these requirements, that your base is positive and not equal to 1, these things will always be true. You'll always have a y-intercept of 1. You'll always have no x-intercept. You always have a horizontal asymptote if y equals 0. And exponential functions never have a vertical asymptote. And then a couple other small things. The function is said to be increasing. And I know we haven't defined this, so I'll give you the short definitions right now. A function is increasing if it gets bigger from left to right. So from left to right, this function is going up, it's increasing. So it's increasing if your base is positive. It's decreasing if your base is negative. Sorry, not negative, if your base is smaller than 1, but still positive. 4 to the x, if we plot some points for this one, just a couple. So if x is 0, 4 to the 0 is 1. If x is 1, 4 to the first is 4. If x is 2, 4 to the second is 16. If x is -1, 4 to the -1 is 1/4. So if we try and plot some points here, I still get the same y-intercept of 0, 1. And then I get the point not 1, 3, but 1, 4, which is a little higher. You can't even graph 2, 16. It's like off the chart. And on the left side, I get -1, 1, 1/4, which is a little bit smaller. So what happens if you're graphing two different exponential functions that have different bases? The one with the bigger base gets steeper faster. So it's going to get bigger faster. It also gets smaller faster, which is hard to draw. This is a great time to point out how useful a tool like Desmos is. So just so you guys can all see this here, let me share my screen. So Desmos, yes, graphic calculator. So just so you can see this looking a little bit nicer, here's y equal to 3 to the x. And here's y equal to 4 to the x. So, I mean, if we zoom in a little bit, you can see that the 4 to the x one, oh yeah, it gets bigger faster. It also, to the left, gets smaller faster. And exponential functions with different bases are always going to cross each other at the y-intercept 0, 1. So, yeah. That's all I wanted to say there.
Our y-intercept is always going to be 1?
As long as we haven't shifted it in any way. So as long as it's just some base raised to the x power, yes.
Okay, thank you.
You're welcome. Let me get back to my notes. And I'm gonna, so the other thing I'll say before moving on to talking about logarithmic functions for a second is that generally, if someone said graph, I don't know, I keep grabbing my less favorite blue pen. When someone said graph, you know, y equal to, I don't know, 5 to the x, I'm typically not going to plot a bunch of points. In fact, usually I'm going to do this. And I'm going to call it good. If this doesn't feel nice to you, that's okay. If you feel like you have to at least plot one more point, James, you can plot one more point when x is 1 and y is 5. But really, an exponential function has this shape. It's increasing exponentially from left to right as long as your base is greater than 1. And it's going to go through the origin. Sorry, it's going to go through the y-intercept of 0, 1. And it's going to have a horizontal asymptote to the left of y equals 0. The only other type of thing that comes up really for these exponential functions is if you were looking at one where the base was between 0 and 1. So I said, you know, graph, I don't know, y equal to 1/3 to the x. The only difference now is that, well, here's the thing. Here's what you should really be thinking about. If you got something like this, 5 to the x, as x gets larger, your output gets larger, right? 5 squared is 125, 5 cubed is 120, sorry, 5 squared is 25, 5 cubed is 125, 5 to the 4th is 625, right? As x gets bigger, the y values get really, really big. But the opposite thing is true here. As x gets really big, the y values get small. right? 1/3 squared is 1/9, 1/3 cubed is smaller, it's 1/27. And so the higher the power is here, if your base is less than 1, the smaller your output's going to get. So what happens graphically is, instead of going up from left to right, it goes down from left to right. And what's actually really kind of interesting here, and I'll probably in the notes later, but I've gotten ahead of myself, oh well, is that really this just looks like a reflection in the y-axis. And it is, because 1/3 to the x is, well, 1/3 is 3 to the negative first power. And when you have a power to a power, you multiply the powers. And we've seen before that when you put a negative on the x, that flips things horizontally. So that this is really just the horizontal reflection of y equal to the 3 to the x, just flipped across the y-axis. Like that. But the bigger point here is that normally when you're drawing these, you don't have to be super duper detailed. When I'm graphing just an exponential function, I really just want like the y-intercept, the asymptote. I guess I should label the asymptote. I have my horizontal asymptote is y equal to 0. And then if you really feel compelled, another point. Okay. The same kind of thing is going to be true for graphing logarithmic functions. You might want to keep this. I'm going to try and keep this on here for a moment so we can compare them. Yeah, let's see if I can get this. So the reason I'm leaving this up here is because logarithmic functions are the inverse of exponential functions. So if I was going to try and graph, say, y equal to log base 3 of x. The important thing to remember, and I guess I should write this down. I feel like now let me go to the other side. I want to leave this here because I want to kind of show you, but yeah, let's go over here. And be a little bit more specific. So logarithmic functions so we're looking at something like y equal to log base b of x. And again, the same sort of restrictions on our base. Our base should be greater than 0 and not equal to 1. And I really want to remind everybody, this really is an exponential graph, except the x and y are switched. Right? If you rewrote this equation as an exponential, it would be x equal to b to the y instead of y equal to b to the x. So what you're really doing is you're interchanging the x and y values. So if I want to graph, say, log base 3 of x, well, I'll remind everybody that's really the same as graphing 3 to the y equal to x. So if I want to find my x and y values, normally I would pick x and find y, but I could also just pick y and find x, right? If y is 0, x is 1. If y is 3, sorry, doing it backwards. If y is 1, x is 3 to the 1. If y is 2, x is 3 to the 2. And then negative numbers too, right? If y is negative 1, x is 3 to the negative 1, which is 1/3. If y is negative 2, x is 3 to the negative 2. It's 1/9. Usually what I would do is I would pick the x value. Be like, oh, x is 1, log base 3 of 1 is 0. If x is 3, log base 3 of 3 is 1. If x is 9, log base 3 of 9 is 2. If x is 1/3, log base 3 of 1/3, well, 3 to the negative 1 is 1/3, and so on. So the point with this graph is that all my x and y things are going to get flipped. Before I had all the points, except it was 0, 1, 1, 3, 2, 9. So I've got 1, 0. It's right there. And 3, 1, 9, 2. And then x is 1/3 and y is -1. X is 1/9 and y is -2. So it looks like this. My graphing is less than excellent. Sorry, that looks terrible. And what I think is worth noting here is that basically all of the x and y properties have interchanged, right? Instead of having I erased it. Instead of having a y-intercept of 1, we have an x-intercept of 1. Instead of having no x-intercept, we have no y-intercept. Right? You can't have a y-intercept because we can't take a log of 0. Right? We know 0 is not in the domain. Instead of a horizontal asymptote like before, we have a vertical asymptote. X equals to 0. And we have no horizontal asymptote. So it's essentially all of the stuff for the exponential function, but all interchanged. In fact, we can even draw it here. Here, right there is your y equal to 3 to the x. And if you'll notice, this is not a coincidence, but these graphs are reflections of each other in the line y equals x. The last thing I'll say, not the last thing I'll say, but the last thing I'll say here is that for a logarithmic function, it's definitely going to look like this as long as b is positive. So it's going to be increasing if the base is positive. Sorry, the base is larger than 1, not just positive, but bigger than 1. And it's going to be decreasing if the base is between 0 and 1. So it's kind of weird. I will say, normally we don't encounter bases that are like 1/2. Like it's just not something that's really done. It's certainly not allowed. It's just very atypical. So while it is very, very normal to graph something like y equal to 1/2 to the x, where it's an exponential function that's going down from left to right. And this is how I graph it. Make sure you draw this so it's not going like straight up, right? It should be going up and to the left. It's very, very strange to graph the logarithmic function y equal to log base 1/2 of x. I mean, it's not that strange. It's just like usually most of the time our bases for a logarithm are either nice integer numbers like 2, 3, 4, 5, 6, 7, whatever, positive integers, or e. And that's kind of it. We really, really don't usually have other bases come into play. If you were going to graph something like this, instead of going up like this, it gets flipped over the x-axis. And we have that kind of graph there. I wouldn't stress too much about this. I'm not prone to asking about anything like that, but it could come up in future math classes. So that's what you do if your base is smaller than 1, is you flip it over vertically. So yeah. Wrong eraser. I have this weird eraser. It's not the right kind of eraser. I keep accidentally trying to use it. So again, you can be as really not precise as you want. For example, if I wanted to graph y equal 2 to the x, you can either, depending on how you're feeling, right, say, okay, well, there it is. There's my point 0, 1. Here's my point 1, 2, if you really felt like it. Or you could be more precise, right? You could say, well, I feel like doing a better job. So I'm going to plot the points 0, 1, 1, 2. If x is 2, y is 4. If x is 3, y is 8. I often don't try and plot too many points that are the smaller ones because once you get close to the x-axis, things just get kind of smushed in. So I'm like, okay, no, it looks kind of like this. And then to the left, it's getting, oh gosh, my drawing skills feel like they're worse than usual today. Like that. I want to be very, 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 very specific here. There isn't a vertical asymptote here. I know I've kind of drawn it so it looks like it's super vertical. It's not, right? I mean, it is super vertical. It's not a vertical asymptote. It is a good idea when you draw this to try and make it look like your arrow is pointing just a little bit to the right as well as going up. Even if you draw it so it's pointing straight up, as long as you don't say vertical asymptote, it's okay, right? There's no vertical asymptote here. And the reason there isn't the vertical asymptote, right, is there's no division by 0. X can be anything, and 2 to any power is always going to be defined. So no vertical asymptotes. And when graphing any of these things, the things you want to keep in mind are, if it's exponential, it's going to have this kind of shape, or it's going to go that way if it's a base that's smaller than 1. If it's logarithmic, well, this is not a great example. If it's logarithmic, like log base 2 of x, it's going to have this kind of shape. And someone pointed this out to me one time, a long time ago, which I think is pretty useful. My hand is not the best for it because I'm old and have lots of lines on my hand. But if you look at your right hand, you might be able to see kind of over your thumb. Whoops, sorry, it's hard when I'm on video because things are backwards. Right, so that's kind of like a logarithmic graph. And that's kind of like an exponential graph. Someone else might have a hand that has more better well-defined lines. But do make sure that if you do this, right, just if you're using this as a memory device, it is your right hand. If you use your left hand, you'll have other graphs that are not the right graphs. So just be aware. Yeah. So with that in mind, we're now going to shift things and stretch things and reflect things. And when we graph them, we're going to make sure that we find the asymptotes as well as the intercepts. So let's take a look at some examples. And that is usually what I'm looking for. When I ask you to graph a thing, my expectation is you find the intercepts and the asymptotes, the vertex if there's a vertex, that kind of stuff. The exception being circles, right? You don't have to find intercepts for circles. So let's graph. Let's graph f of x equal to 4 to the x plus 1 minus 5. So here's what I see right off the bat. This is going to shift us left 1 and down 5. So it's going to look like the usual 4 to the x graph, and maybe I'll draw a few graphs here. So here is 4 to the x. And I'm going to shift it 1 to the left. So typically when I'm shifting things, I try to think about where like a middle point goes. Either like, where is my y-intercept going to end up? Or where is my, if there's an origin, where is that going to end up? So I'm going to shift it 1 left. So that point 0, 1 is going to move 1 to the left. It's now going to be at -1, -1. And the point that would have been 1, 4 is now 0, 4. It's kind of interesting. And then we're going to shift it 5 down. So -1, 1 is going to move to -1, -4. So I'm going to go down. So I see that this point at -1, 1 is going to end up at -1, -4. If I move 0, 4 down 5, it's going to end up with 0, -1. And both of those are moderately important, but the one that's actually the most important is what happens to the horizontal asymptote. So when we shift a graph left or right, its horizontal asymptote doesn't change, right? Because you're just taking a horizontal line and you're shifting it left or right. It's still a horizontal line. When you shift it down, when I shift it down 5, my horizontal asymptote is going to get shifted down 5. So instead of being y equals 0, my new horizontal asymptote is going to be y equal to 0 minus 5. So down here at -5, I have a horizontal asymptote. So I have, let's see, something that looks like that. I already have my y-intercept because I saw where something shifted. But if I didn't have my y-intercept to start off with, like if I hadn't noticed that 1, 4 ended up at 0, 4 and then went down there, right? Then we would actually go ahead and find our intercepts. So to find the x-intercept, find the y-intercept, we're going to set x equal to 0. Setting x equal to 0, we're going to get y equal to 4 to the 0 plus 1 minus 5, which is 4 minus 5, which is -1. Which we already knew, but still good to talk about how you find things. The x-intercept, on the other hand, is a little bit more work. Now, first of all, there is an x-intercept, right? Because if you shift an exponential graph down, there will now be a place where it crosses the x-axis. To find it, we're going to set y equal to 0. So setting y equal to 0, I have 0 equal to 4 to the x plus 1 minus 5. That's going to be a little bit gross. I'm adding 5 to both sides. You got 5 equal to 4 to the x plus 1. I would probably use natural log, but you could use log base 4 if you wanted to. I would say the natural log of 5 equals the natural log of 4 to the x plus 1. We're out of room here. I would then bring down the x plus 1 to the natural log of 5 equals x plus 1 times the natural log of 4. Divide by natural log of 4, subtract 1. So x equals the natural log of 5 divided by the natural log of 4 minus 1. Not a very nice number, but a number, a positive number. Okay, where'd you go? Let's look at some more examples. What do I got here? Let's look at this graph. N of t equal to 2e to the negative t minus 2. Okay, and this is right. You could use y, you could use f of t. This is notation. If you're especially taking the 17 series, you will often see functions called n of t for like the number of things you have at time t, because there's a lot of biological examples in the 17 series. So this is a typical function notation. But what's this going to do to our graph? So let's start off with, well, what does y equal to e to the t look like? So e is the kind of common base that comes up that's not an integer or a fraction, right? E is about 2.7. So it's going to look, and here's just e to the t. Right, there's y equal to e to the t. So what's the negative going to do? What is e to the negative t going to look like? Which way is it going to reflect? Is it going to reflect horizontally in the y-axis or vertically in the x-axis? If I'm looking at now y equal to e to the negative t. Well, here's what I'm thinking about. I know that no matter what t is, e to the something is still going to be positive. Basically, here, if you plug in, say, 2, you get 2 comma e squared. E squared is like about 8. Or here, if you plug in negative 2, you get e to the negative 2, which is e squared, which is about 8. So this is definitely giving you the reflection horizontally in the y-axis. We put the negative, right, when the negative happens to the variable before, like, you do the function to it. So there's your e to the negative t. The 2 is going to stretch it vertically by a factor of 2. Right, so everything's going to get stretched up by a factor of double. The smaller it is, though, the less it's going to get stretched up. So, right, I'm going to try and do this. So there's our 2e to the negative t. Right, all the y values got doubled. And since they were all positive, they all moved to be twice as far away from the x-axis as they were. And then finally, this minus 2 is going to shift everything down by 2. So I also want to point out, when you're drawing these, you don't have to draw like every intermediate graph. I'm just drawing them to show you guys what is happening. But we'll finish this one and then I'll kind of talk about what I would normally do if I was just trying to draw it. So let's see. This negative 2 is going to shift it down 2. So this point 0, 2 is going to shift down to the origin. And my horizontal asymptote that was y equals 0 is now going to be 2 less, which is going to be negative 2. So it's going to look like this graph and move down 2. So it's kind of hard to draw at this point. Whew. That's not my best graph ever. I will also remind you all, Desmos is your friend. There are lots of graphing tools. You are not forbidden from using them to kind of see how things should look. If I were graphing this without kind of showing all the steps, what would I have done? I probably would have said, well, I'm going to shift down 2. And I know the negative is going to make it go down from left to right. And then I would have worried about finding my intercepts. So to find my intercept, I would say, well, my y-intercept, if I set t equal to 0, I plug in 0 here. And then 0 is 2 times e to the 0 minus 2. E to the 0 is 1. 2 times 1 minus 2 is 0. So, oh, my y-intercept is the origin. And since the function is either increasing or decreasing, it can't have more intercepts. And since I know it's decreasing because of that, or it's flipped, either way you want to say it, I know it's got to look like this. So I'm really just kind of finding the bare minimum of features, the asymptotes and the intercepts, and then looking at the shape and trying to just make the graph fit those points. I'm not trying to draw too many other points if I don't have to. All right, let's look at a logarithmic example. Let's see. Let's look at this one. Let's graph y equal to log base 2 of x plus 4 minus 2. Okay. So I know my usual logarithmic graph looks like this. I know that the plus 4 is going to shift it left by 4, and the minus 2 is going to shift it down 2. So I'm going to try and do it all at once. Well, for logarithmic graphs, normally the vertical asymptote would be x equals 0. Because I'm shifting it 4 to the left. And my vertical asymptote is x equal to -4. And here's the thing. Since I've shifted it to the left, I'm going to end up having a y-intercept because it's going to do this kind of deal and cross the y-axis. It's also going to have an x-intercept because it's going to have to cross the x-axis. So we have both the intercepts. So we should probably figure out how it's going to look. I'm not going to ignore the -2, but like, so if you take this kind of graph and shift it down 2, it doesn't like look a ton different, right? It just kind of, it's harder to see the vertical shift in a logarithmic graph. But what we can do instead is kind of say, well, I'm going to find where the intercepts are and then graph the right shape through those intercepts. So let's find the y-intercept. Set x equal to 0. Y is going to be log base 2 of 0 plus 4 minus 2. So that's going to be log base 2 of 4 minus 2. Log base 2 of 4 is 2. 2 minus 2 is 0. And again, when you have a function that's increasing or decreasing, you can't have more than one x-intercept. So since this is an x-intercept, it's our only x-intercept. So our graph is going to look like this. That looks okay, actually. You could find more points, but if you really, really, really wanted to make a table, no one's stopping you. I'm going to pick values like if x is -3, y is going to be log base 2 of 1 minus 2. Log base 2 of 1 is 0, 0 minus 2 is 2. Or I could pick something like -2. And log base 2 of 2 minus 1 would be, sorry, minus 2 would be 1 minus 2, which is -1. So right, there would be points like this. -3, it would be -2. -2 would be -1. And then if you plug in something like, I don't know, plug in 4, log base 2 of 8 is 3, 3 minus 2. So clearly you can see, well, maybe not clearly, I don't know. Maybe you can see that my graph is not really to good scale, right? Like this is supposed to be 1. So, but that's okay, right? That's what I'm really trying to say is, as long as you got the right shape, meaning it looks appropriately logarithmic, and you've got the right intercepts and asymptotes, you don't need all these other points. I don't want them. You don't want to find them. So, yeah. We got time. Let's do a couple more. I want to graph, say, f of x equal to log base 3 of x minus 1. So it's going to be my usual logarithmic graph, shifted 1 to the right. And the way, especially for logarithmic graphs, it's kind of easy to see which way it should shift because of the domain. Right? For a logarithmic graph, the domain is that the insides have to be greater than 0, which means x is greater than 1. Normally, the logarithmic graph would have a vertical asymptote of 0, but now we shifted it 1 to the right because now x has to be bigger than 1. And the normal x-intercept of x equal to 1 is going to get shifted 1 to the right and be x equal to 2. If you don't like just saying shift to the right, though, you can also find it. Right? To find the x-intercept, we set y equal to 0. So 0 equals log base 3 of x minus 1. Rewrite this as an exponential equation. 3 to the 0 equals x minus 1. But 3 to the 0 is 1. Add 1 to both sides, and x is 2. So there's our graph. Again, I've probably drawn it not great. It's probably a little too exaggerated. It's okay. As long as your graph has close to the right shape, it doesn't have to be super, super precise. But I probably often end up drawing my logarithmic graphs growing too rapidly, right? They usually kind of flatten out a lot sooner. I will say they don't actually flatten out. They just don't increase so rapidly. And it should probably look more like this. But I really want to point out there's no horizontal asymptote here. Right? This keeps getting bigger and bigger and bigger and bigger and bigger and bigger forever and ever and ever and ever and ever and ever. It just does it really slowly. I feel like I had one more example I wanted to mention. I mean, I'm out of examples on the notes. That's okay. I can make up examples. Yeah, I got one. Yeah, let's graph y equal to log base 9 of x plus 2. Yeah, is that what I want? Sure, why not? That seems fine. Okay, again, same sort of deal. We're trying to find, well, we know the shape. The shape is the usual up and to the right shape for a logarithm. And we're trying to find all the things. The vertical asymptotes and maybe some intercepts. There's definitely going to be some intercepts here because it's shifted to the left. Right? We're going to shift left 2. So our vertical asymptote is, here's a tip that is true. Why would I give you one that's false? I don't know. Here's the thing that's true. When you're finding asymptotes for vertical asymptotes for logarithmic functions or horizontal asymptotes for exponential functions, it's always just how much that kind of shift you have. So if in your logarithmic function, if you have a shift that's 2 to the left, your vertical asymptote is 2 to the left. If you have an exponential function, which has a vertical shift of like 2 up, your horizontal asymptote is going to move 2 up and be y equals 2. So that's kind of, it's an easy way to think about what the asymptote should be. So our vertical asymptote is negative 2. You can also think about for a logarithmic function, just what makes the inside of the logarithm equal to 0. That's going to be your vertical asymptote. Oh, it's x equals negative 2. Great. So then I would start drawing it. There's my vertical asymptote at x equals negative 2. And unless something else funky is going on, the x-intercept should also just get shifted 2 to the left. So normally it would be a positive 1. It's going to shift 2 to the left and be a negative 1. You can also find it by, again, setting y equal to 0. So if you set y equal to 0, you get 0 equal to log base 9 of x plus 2. So 9 to the 0th equals x plus 2. So 9, which is to the 0 is 1, minus 2 equals x. So x equals negative 1. And then we can also find the y-intercept, which is not going to be very nice. So finding the y-intercept here, sure. The y-intercept, we're going to set x equal to 0. If I set x equal to 0, I'm going to get log base 9 of 2. I don't really care what this number is. I know it's a number. I know it's smaller than 1. I know it's positive. So there's 1, and this number is smaller. You can get out a calculator. I'm not going to approximate it. I'm just gonna say, well, I'm gonna draw my picture. Perfect. I'm sure I got it exactly right. Or not at all, which is okay. But right, as long as it looks reasonably like it's in the right neighborhood, you're good to go. All right.